Okay, the next example of series that we'll talk about are called telescoping series. And you may remember as a kid, you've seen telescopes, right? And they kind of, they actually collapse in on each other, right? So you can actually push the telescope in, everything kind of collapses into a small piece. Everything kind of disappears, and you're only left with the first and the last piece. Everything kind of disappears in some sense. So this is the idea with these series. They kind of collapse. So the series collapses. The infinite terms in the series, they all collapse. And this allows explicit calculation. Okay, so here's what a telescoping series is. It's of the form sum from n equals 1 to infinity of an plus 1 minus an. Okay, so it means that if I write it out term by term, it's a1 plus 1 minus a1, a2 plus 1 minus a2, 3 plus 1 minus a3, and so on. And we end, let's say, we sum until n. So let's say I stop here for my partial sums before I take my limit. So here's what's going on. Notice that a1 plus 1 is actually a2. So these terms are actually the same and they cancel, because there's a minus sign in front of the a2. There's a minus sign in front of the a3. There will be a minus sign in front of a4. In fact, everything collapses in on itself except for the last term and the first term. If that was kind of hard for you to see, let me just do n equals 2. So a2 minus a1, and then we have plus a3 minus a2. And I'm going to cancel the a2s. I'm left with a3 minus a1. This happens in general if I just replace 2 with n. So that means my 2 plus 1 becomes an plus 1 minus a1. If it holds for 2, there was nothing different about the procedure with general n. So we end up with this, first and last. So in other words, my partial sum of the series is actually equal to an plus 1 minus a1. So it's just the first, it's the last minus the first. It's just like a telescope in that sense. It collapses, everything collapses, and you end up with an object that looks like the first and the last. So therefore, the infinite series is equal to a limit as n goes to infinity of an plus 1. And then it's minus this finite term, which does not contribute to the divergence or convergence. So all you need to do is just evaluate this calculus limit to evaluate the sequence limit. And we already discussed techniques to do this in the previous lectures. So how about we just consider a couple examples of a telescoping series. So here's one, the sum from n equals 2 to infinity of 1 over square root of n minus 1 over square root of n plus 1. Now, this is actually a telescoping series in disguise. So in disguise, because a telescoping series generally has this form, right? An plus 1 minus an. But you see the plus 1 is actually before the plus 0. So I'm just going to add a minus sign. So minus my infinite series is going to be equal to the infinite series of an plus 1 minus an, where an is actually now equal to, let's say, 1 over square root of n. And I suppose you could just keep a minus sign there, and you can make my an plus 1s look negative, like so. But let's just make it positive for the sake of this lecture. So as before, the partial sum is going to look like n equals 2 to n. So then I'm just going to write out first few terms. So it's 2 plus 1 minus a2, a3 plus 1 minus a3, and we go all the way up till an plus 1 minus an, and I'm going to cancel everything before except for the first and the last terms. So it's actually just equal to an plus 1 minus a2. So the sum from 2 to infinity of my series is just the limit of the partial sums. So it's just a n plus 1 minus a2. So if I just plug it in, I should just get the limit of 1 over square root of n plus 1 minus the 1 over square root of 3. So this should go to 0. And I should just get minus 1 over square root of 3. So therefore, my original series, without the minus sign, it should just be the first term. So 1 over square root of 3 with a negative sign. Okay, so really it was just this term at n equals 2. Okay, there's one more example that I want to mention, and that is the fact that this is actually a telescoping series in disguise. So here's how you do this one. So there's a trick, and you can look this up later if you want. This is called partial fraction expansion. We'll be talking about this later in the course, but we won't need it in its full glory. You're free to just use this trick. So 1 over n times n plus 1. This is free to use. You can use this trick that says that this is equal to 1 over n minus 1 over n plus 1. So the product is actually equal to a sum over these factors. And this is easy to check. So 1 over n minus 1 over n plus 1, if I just clear the denominators or cross multiply, then I see this is n plus 1 minus n divided by n times n plus 1. The key point here, in fact, is that this cancels. So we end up with 1 over n times n plus 1. So now you can see that for an equals minus 1 over n, the series is telescoping. And you can guess that it should look like 1, because this is the first term, or rather it's negative the first term. And it's a similar calculation as to before. Okay, that's telescoping series. And in the next video, I'll talk about geometric series, which are actually just telescoping series. It's in a kind of different sense. Well, I mean, I think it's still telescoping, but nobody calls it telescoping, but it's the same idea. But wait, I think the reason I want, yeah. So I wanted to say this also. So why it works. Here's another reason other than just seeing that it works, maybe I can make it less mysterious for you. Remember that the fundamental theorem of calculus it says that the integral from let's say a to b of f prime of x dx is equal to f of b minus f of a. So you can think of this as the last and first. Kind of similar to what we've been seeing, right? Well, in fact, remember that a derivative is equal to a limit of difference quotients. So it's f plus x, f of x plus h minus f of x divided by h. The key here is the difference, of course. That's why I'm mentioning this. And this can be parallel with the telescoping series, which is also a difference. Instead, it's so that you can think of it as like a derivative in n. So this is like very much in quotation marks ddn of an. In reality, you might see this later on in your other courses. You can think of this as the difference operator of an. And so what this is saying is that the integral of a derivative is equal to the last minus the first. It is just an entirely analogous idea. In fact, this telescoping, this is actually used to prove the fundamental theorem of calculus. It is it's complete. It should be completely unsurprising once you see that. If you ever see that proof, it should be completely unsurprising now that telescoping series work like this, because whenever the entire point of integration in calculus is to integrate perfect derivatives. These are the only ones we actually can integrate. So similarly, our series are very easy if we can write them as telescoping series. Okay, thank you for watching.